Okay, so this is an example of a combined gas law problem. And sometimes people can't tell whether they should use the combined gas law or the ideal gas law. So the key way to tell is you ask yourself, is something changing? If something is changing, then you need to use the combined gas law. So in this case, we have a balloon and it has helium. It occupies this volume, 2.3 liters, at this pressure and this temperature. And then we want to know what will its volume be at STP. We'll talk about STP in a moment. But the idea is its volume is changing. So if its volume is changing, the ideal gas law, PV equals nRT, is not going to be sufficient because that only has one volume term. And we've already got that right here. So we need to use the combined gas law, which is when something is changing. And the combined gas law, again, is P1 times V1 equals over T1 equals P2 times V2 over T2. And that's the combined gas law. So again, always start by writing down everything you know. So it tells us the balloon occupies this volume, 2.3 liters, so that's we'll call V1. We could just as easily call it V2, but we might as well call it V1. At this pressure, 825 millimeters of mercury, so we'll call that P1. And at 70 degrees Celsius, T1. Okay, so that's what we know so far. And it wants its new volume, so our volume V2 is unknown. We can put a question mark at STP. Now this is something we just kind of have to know. We use it a lot. Standard temperature and pressure. Standard temperature and pressure, the pressure is 1 atmosphere, and the temperature is, strangely enough, 0 degrees Celsius is the standard temperature. So 1 atmosphere is 0 degrees Celsius. Anytime you see STP, that is what it's referring to. So basically, we know everything except V2. So we're going to use this equation and solve for V2. But again, we have to check our units. The key thing is you can never use Celsius in any gas law problem. You have to use Kelvin. So 70 Celsius, we might as well just make the conversion right away. Plus 273 is 343 Kelvin. So I'm just going to write that down. 0 Celsius is 273 Kelvin. I'm not going to use 0. If you tried to use 0 in this problem, you'd run into a surprise when it didn't work because you can't divide by 0. All right, now pressure. When we did the ideal gas law, everything had to be in atmospheres. It actually doesn't matter for these problems as long as the units are the same and can cancel. In other words, 1 atmosphere is the same as 760 millimeters of mercury, so I'm just going to use that for the sake of demonstrating this problem. So I know everything except V2. So I have my equation, I'm going to solve for V2. So algebraically, if I rearrange this equation here, I can get that V2 is going to equal P1 times V1 times T2 divided by P2 times T1. And if we look at this for a second, it should make sense because the volume is going to equal a volume, and these units need to cancel. The pressure is going to cancel the pressure, the temperature is going to cancel with the temperature. But let's actually see that in action. So V2 is then going to equal P1, which is 825 millimeters of mercury, times V1, which is 2.30 liters, times T2, which I said was 273 Kelvin, over P2, 760 millimeters of mercury, times T1, which is 343 Kelvin. And if I've done this properly, I will notice the units, pressures cancel, kelvins cancel, and I'm left with liters. And notice, as long as these pressure units are the same, it works out. You might say, well, why don't Celsius work out again? I would get an answer of 0 if this was in Celsius, which is not going to work out for us. So 825 times 2.3 times 273. Again, make sure you do order of operations properly when you divide, or it will not work. So when I do this all out, I get V2 equals 1.99 liters. And once again, if I want to check my answer, I can plug this back in to this equation. I can put them both in. I should get the same number. I will leave that for you to do. I think you guys can handle it. But anyway, that's my final answer on this problem. So until next time, I am Derek Genova. Have a delightful day.